welcome everybody this morning from wherever you're attending for this presentation. Today, we're going to be covering the topic of the future of servers in industry. Now, what I will do is I'll just quickly introduce myself again. For those of you that have attended some of these presentations previously that I've actually presented, this will probably be something that you might not necessarily want to pay too much attention to. I've been with the company since 2008, and 2008 in this case for this presentation is going to be hopefully a bit of a good year, because it's going to provide a starting point, and it's going to give us some context about some of the information that we're going to be providing as this presentation unravels. I've spent a few years in product management, a few years in business development, and currently I'm the sales leader for Aonline. My email is right there, richard.ronsett@advantech.net.au. So like always, if you've got any sort of questions that you want to raise during this presentation, by all means, please feel free to do so. I'll try to answer those as well as I can, as accurately as I can. Otherwise, if there are any questions or queries that come up afterwards, by all means, feel free to drop me an email and I'll look to try to get that information for you as soon as possible. So what are we going to cover today? Here's what we're going to look at. We're going to look at the future of servers in industry, and that means that we're going to be putting a little bit of context around it, including a bit of a snapshot about the history and the evolution of industrial computing. And that means we're going to be looking at the advancements, particularly when it comes to things such as processing power and connectivity. We're also going to be looking at the topics of what are the performance drivers when it comes to computing, as well as the key points of difference when it comes to higher performance server level processing versus embedded. Now, when I say that we're going to be contrasting things against embedded platforms, that's exactly all we're going to be doing. We're going to be contrasting them to give us a bit more perspective. We're also going to take a look at the current and also the future applications that exist in industry, and the applications that are geared towards higher performance platforms. And that means we're going to be looking at workstations, high performance computing, high capacity storage, as well as we're going to start looking at the topics of GPU computing, machine, deep learning, as well as we're going to look at scratching the surface of AI applications. We're going to take a look at some of the current boards that we've got to offer that provide the foundations for that. And we're also going to take a look at some of the case studies. Now, before I do move on, one of the things that I will say here is that when we talk about servers out there and what the future of servers are, is that the term server is, depending on where you come from and the language that you use, server is a term that is used quite loosely in a lot of places. So even though the definition of a server is a computer platform that provides services to, let's say, client systems or client devices, we're going to be not only looking at those aspects of server platforms, but we're also going to be looking at the higher performance applications as well for client side processes and applications, such as those 5 listed there. But one of the first things that we want to do is we want to look at where high performance computing fits in when it comes to the server side of things. Now, we will be looking at a very, very short look at some of the boards that we supply, because when it comes to the higher performance computing side of things, as you can see here on the screen right now, we refer to them internally as our Sky servers. Now, a Sky server is primarily composed of 2 real key components. Firstly, you've got the high performance chassis, which is our higher end, most flexible, most capable 1U, 2U, 4U platforms, which then marry up with an Advantech server grade or an ASMB motherboard. Now, for those of you who've bought industrial systems, industrial chassis from us previously, you may also be familiar with the AIMB series, the Advantech industrial motherboards. They're no lesser or greater than the others, but the ASMB series typically go a bit further, including specifically support for Xeon and server-grade CPUs, and having the support there for ECC and registered memory in order to provide those high availability systems. When we look at the Sky servers, where do they fit in? Well, at a very, very high level, especially when we start thinking about Corona and all that sort of stuff and critical infrastructure and non-essential businesses, it's really the critical applications, particularly where we start thinking about fault-tolerant failover systems, all the way through to high-performance applications, starting to get into artificial intelligence and GPU applications. We are not going to go too deep into the technical stuff here. This presentation is actually probably going to be lighter on the tech and probably a bit more about what is coming. So when we think about Advantech and what we can do within industrial systems, we have what we call the 357 service guarantee. And that means we offer the 3 levels of service, whether it be from the first level with dedicated application engineers here in Melbourne to help determine what certain solutions can be, through to fault finding, all the way through to second level and third level support. We also have the 5-year extended warranty capability. So that means we can service products, particularly early in their life cycle, longer into the future, as well as the 7-year product life cycle, which allows your applications to have a certain amount of stability that aren't necessarily available, particularly when coming up with platforms using commercial grade equipment, which has a much faster evolution cycle. So when we look at why we provide our boards the way we do, okay, firstly, there is the difference between the commercial grade there. Now, our boards are typically good for 0 to 40 degrees. They have a higher vibration specification. So, and you might be wondering, for instance, why an industrial server would have a vibration specification considering where they normally or traditionally live. But it's still, that is a capability that has carried over, particularly from the last decade. We've got higher technical support, we've got that longer longevity, not to mention the revision control as well. So when we align it, so when we superimpose ourselves against our competitors, the real big key factors there that I've highlighted in red is that we've got better tech support, we've got that longer life cycle compared to the commercial boards at only 1 to 2 years. We've got that revision control, the warranty, not to mention those industrial features. Now, one of the things that we were going to cover, particularly in the agenda, is we're going to look at the history and the evolution. And that means for this part of the presentation, I'm going to go back in time a little bit here. Okay, I did mention that 2008 was a pretty good year. And in 2008, as you can see there on the right-hand side, we've got, for people who know what they're looking at and can identify some things, we've got a pretty old type of board. Now that board there was the AIMB 742. It was in big circulation in 2008. In fact, the reason I picked this one out is because 12 years ago, this was a board that we sold by, by the shipping container load, proverbially. Now, what did it have? It all ran on an old style socket 478 Pentium 4, single core processor running at 2.8 gig, had an AGP slot there for your graphics cards if your application needed them, 5 PCI, 2 ISA, ran first generation DDR memory, only had 4 gig capacity, 2 Ethernet ports, serial, USB. And when we think about this today, the question that we start to ask ourselves is, well, what's the big deal about it? The big deal is when we think about how computing has evolved. Now, what I've got there on screen is a product that has traditionally superseded and replaced a lot of the industrial systems there as an embedded fanless platform. This one here is the UNO 2483. Now, The UNO 2483 started circulating within our range around about 2015. So even this, which we've still supporting up until 2019, I think we're still even got that available for sale today, is based around fourth generation i7 architecture. And that there, 1.7 gig, it's dual core, 8 gig of memory, which is 4 times the speed, 4 gigabit ports, which gives us 20 times the network capacity, not to mention the serial ports and the USB offerings as well. So when we put this together, we can see that already on paper, things have started to move forward, but to really visualize it, what we want to do now is I'm going to zoom out and I'm going to let you see things in a bit more context. So what I've got here is some processor performance. Now, I haven't actually used a benchmark here because although I've got absolutely nothing against benchmarks, benchmarks sometimes offer a little bit of bias. Some processors are better at certain tests than others. So what I'm using here is a unit called the FLOP, or the floating operation per second. Now, before this turns into a complete math lesson, a FLOP is calculated by the number of processing units. Usually that's going to be 1. Multiply by the amount of cores on that processor unit, multiply by the clock speed in hertz. So when we start talking about megahertz and gigahertz, this number starts to get really, really big. Multiply by the amount of operations per second that that processor can actually execute. So when we look at the left-hand side of this, of what's on the screen right now, we can see the CPU performance in the amount of floating point operations per second that it can actually achieve. On the right-hand side, we've got power consumption. So we can basically see what the cost is for it, in effect. Starting at the bottom, 10 to 12 years ago, where the Pentium 4 2.8 processor was the staple of what we were providing to industry, that Pentium 4 processor was capable of around about 5.5 billion operations per second, or 5.6 gigaflop. Did it by consuming about 54 watts worth of energy. In 2013, an embedded computer running a fanless or running a mobile Core i7 was putting out around about 46 billion operations per second in terms of its processing power. And it was doing it on around about 1/3 the power budget at 17 watts. The UNO 2483, which we've just seen earlier, being fourth generation, now takes that processing power up to over 100 gigaflop and does that for 15 watts of power. And that came into effect in 2015. When we add more context around that, a more recent entry-level processor such as the Atom E3845 quad-core processor was producing around about 15 billion operations per second, whereas the current 6th generation mobile processor is once again over 100 billion operations per second in terms of its capability. And one thing that I'm going to try to get ahead of here is there could be the question of, okay, why is a 6th generation processor on par with a 4th gen CPU? The reason being is that the 6th gen architecture has been slightly modified to accommodate Windows 10, whereas the 4th gen was capable of running it, but not optimized for it. So while we're in deep information, we can see here that as we add more and more current level of processing, particularly when we start getting to 7th generation desktop, the 7th generation i9, the 7th generation 9000 series, and then the Core i9s, which are desktop, we can see that the processing power, as well as at the top end, although the power consumption goes up, the processing power has gone from, when we look at the 7th generation, to around about 280 gigaflop up to 630, 640 gigaflop. Now, short of just saturating you with all this technical jargon and massive words, what we can see is that in the space of 12 years, in the space of only 12 years, the entry-level processor is doing 3 times what we were doing 10 years ago. An embedded platform using the 6th gen processor is now 20 times more powerful than the desktop platform, and the current desktops are over 100 times more powerful than what we were seeing as little as 10 years ago. So the question that I thought was worth asking is, what is driving all of this performance? And I think there's really 2 factors. The first one is consumer grade, basically gaming systems. The more powerful the software is getting, the more powerful the computers need to be, the more powerful the computers are capable of being, the more powerful the software can be. The second thing is when it comes to industry, and we need to go back a few buzzwords here, considering that we're starting to scratch around in AI. We're heavily involved in Industry 4.0 and IoT. A few years ago, the big buzzword was cloud. The big driver here was big data, when we started being able to collect massive amounts of information, where at the time, a lot of people didn't really know how we were going to use it. So what are the key points of difference, particularly when we start looking at the desktop or the server grade platforms versus the embedded style of computing? First things first, the processing power has grown by 48% year on year for the last 12 years. Now that 48%, that's a bit of a coarse figure. It depends on what you're comparing it against. But imagine what 48% growth would do to any aspect of your life, and given the space of 10 to 12 years, you're looking at 100 times where you were 10 years ago. The next thing we do see is the form factor, where not only are things getting more powerful, but we're seeing a reduction in the physical space that computers are taking up, particularly when it comes to the embedded fanless platforms. And that means not only are we driving computer performance further and further, but with less moving parts, with fanless architectures, there's more computing power filtering down to the lower levels of business and lower levels of industry with even more reliability. And that changes how rack space in the server areas is being used. Not to mention the fact that we've got more connectivity due to chipset performance, but we've also got more expansion. And this is really now where the server grade or the rack mount platform really comes into its own, because the expansion there is much more flexible, particularly when it comes to PCI Express. And when integrated with the right casing, with the right chassis, we can start looking at things such as full length, full height expansion cards, particularly when it comes to graphics arrangements. When it comes to the chassis side of things as well, being far more flexible platforms compared to embedded, they offer different arrays of storage and storage configurations. But the question really is, with all of this power and all of this capability, where do servers in the future, where will they fit in? And the real key applications are going to be in higher power apps, such as clusters, failover arrangements, cloud infrastructure, GPU platforms, workstations, storage servers, research applications. The list is quite extensive. So what we're going to do now is we're going to start taking a bit of a look at workstations. And when I talk about workstations here, I'm talking about a high performance system that you would use almost as a desktop, particularly when it comes to the design and visualization, because especially once you start marrying up and using that flexibility, let's say with higher power graphics processing in order to render three-dimensional images, which CPUs such as Atoms really can't do, they're not optimized for. You've got the ability to offer yourself and your industry, your business, tremendous amounts of display real estate. And that allows industries that are involved, particularly in design and simulation, product optimization analysis, such as here it looks like we've got a compressor impeller there, which looks like it has finite element analysis, pressure gradients on one side as well as flow dynamics on the other. It allows higher power platforms to do much more analysis virtually while increasing accuracy and doing the information visualization rather than going through the process of physical trial and error. The next element that we're looking at is high performance computing. Now, when we talk about high performance computing, the old word for it used to be supercomputing. And this is where we start to do things based around numerical simulations for things such as research applications, social modeling, all sorts of different aspects. High performance computing, particularly when it comes to high capacity boxes and high capacity server boards, is where we start to look at things such as virtualization applications, where you can start to allocate resources or have high resource in a certain system. And you can then start running multiple environments within a certain bit of hardware. We start looking at things such as failover platforms for high availability. You may be aware of a phrase called the 5 nines of availability, where an application that is available for 99.999% of the time only experiences downtime of around about 5 minutes per year. This is the type of thing where critical infrastructure, particularly in the financial sector, make use of. We're talking about high performance for things such as blockchains. And in this case, no, I'm not necessarily talking about the cryptocurrencies, but I'm talking about the technology of being able to distribute computing power across larger arrays, or what they're called grids, in order to maintain ledgers, particularly for auditing and reporting purposes. Not to mention the resource allocation that goes into things such as virtualization as well. The next area that we're looking at is the storage server. Now, a storage server is exactly as it sounds. It's a server that stores data for a number of client systems. And these storage servers actually form predominantly the main architecture behind cloud computing and cloud storage. So considering that cloud is so accessible now, why would we look at a storage server? First things first, like a lot of the applications that I'm talking about here, whether it's for display workstations, whether it's high performance computing, storage servers are not for every single company or agency out there. But the reason that I've put a security camera in there is, once again, to paint the picture of how data is increasing. And storage servers, particularly at the local level, allow a much more convenient and much more speed of access, because bandwidth is nowadays, particularly when we start talking about 5G, when we start talking about all of the different IoT bands out there, bandwidth for large file sizes is a major driver of industry. Now, to put some numbers around that, and this is an experiment that I actually did while I was compiling this presentation for all of you, is if you take a full high def image, so 1920 by 1080, and you expand that to 4K size, 4096 by 2160 on the screen, when you double the screen size, you actually have 4 times more image. And depending on things such as software, that means there's 2.5 to 4 times more file size. So particularly when we start thinking about applications such as the video surveillance, the security market, in order to be able to store that data, there is that compromise. Do you go for lower resolution? Do you go for video compression? Or if you want that high accuracy 4K security platform out there and you want that information to be available for a certain amount of time, whether it be 1 week, 2 weeks, whatever that is, you need the capability of storing that information. Not to mention, when it comes to having that information there, I'm going to move on. that's when we start talking about individual file size. Now, although cloud infrastructure can probably hold that, individual networking, when it comes to the local industry, when it comes to the local area, whether it be gigabit or whether it be 10 gigabit networks, are going to be able to retrieve that file and make it available for viewing and modification much quickly than, let's say, your internet connection. So there's definitely room for storage servers depending on what you're looking at. Not to mention auditing and reporting, storage of data files, as well as holding information for augmented reality applications as well. So this is probably one of the first times we're going to be looking at an individual product here. And I've put this one in here because the HPC 8424, you only need to take a look at it to realize that it's a bit of an animal. It's 4U rack mount chassis, full depth. So this chassis is capable of taking a full extended ATX board all the way down to ATX, micro ATX form factors, depending on what you need this thing to be capable of doing. But just taking a snapshot at the front of it, you can see there's 24 drive bays capable of 3.5-inch disk storage. Now, to put some numbers on that, typical drives out there in the 3.5-inch form factor are now capable of 10 terabyte. So depending on how much storage you need, as well as the arrangements that are there, in 4U rack space, you've got 240 terabytes worth of storage. So if you're in the video surveillance market, this is something that could be very, very attractive, especially when there's especially over large geographical installations where you've got high resolution cameras having high frame rates being recorded. So to put that into a bit of context, when we were talking about bandwidth, NBN, I think in Australia, offers a maximum speed of 100 megabit, which allows you a theoretical transfer speed of 12 megabyte per second. A local gigabit network, which most offices, most organizations will have, boosts that speed by a factor of 10, allowing you to get information out at 120 megabyte per second. So it allows having that local infrastructure, although there is the upfront cost, it's very, very powerful. And not to mention that this box as well also offers 4 slots for NVMe drives, which allows even faster data retrieval at the local level because of the technology behind that using PCI Express versus SATA. Now, one of the big things driving the future of servers in industry is when it comes down to GPU computing. This is a little bit of a pet subject of mine, but no matter how much I look at it, I'm only ever going to be so good on it. What is GPU computing? Well, fundamentally, it's the use of massive core counts to create high-powered numerical processing platforms. There's nothing more, there's nothing less to it. The question is why? And it's all about being able to rapidly process massive amounts of real-time data. And what GPU computing does is it starts to open the door to things such as artificial intelligence training through machine and deep learning, particularly when it comes to things such as pattern recognition, subsequent predictive analytics, as well as training for inference servers, allowing augmented and visual reality applications where virtual reality is a completely virtual environment, whereas augmented reality, as you can see there in the right-hand side, is being able to take in the real-world environment and then overlay additional information that complements what you're seeing. So in terms of GPU computing, we're going to go back to probably some of the colder data. Is what does it offer? Now, earlier, depending on your memory, you might remember the i7 7700K and the i9 9900KS processors running at around about 280, 640 gigaflop. Before I show you the power that a graphics card offers, particularly when it comes to processing visual information, I've put here the Xeon 8180. It's a socket 3647. It's one of the Intel scalable processors. Now, that processor there, the i7-9900, that's an 8-core CPU. The Xeon is actually a 28-core CPU running at around about 205 watts. That actually offers over a teraflop of performance. However, when we put that against a graphics card that is set up for that, we can see the contrast there where the NVIDIA V100 offers a massive 14 teraflop of performance. And I mentioned that it runs on massive parallel core counts. That i7-9000 processor ran 8 cores. The Xeon ran 28. The NVIDIA V100 has 5,120 cores on there, all working together. To put that into a bit more of a easier, digestible format, imagine how long it would take one person to build a house. Now imagine 1,000 people building a house, how quickly it happens. So we're now going to start scratching the surface of machine and deep learning. There's a ton of information out there on this. It's very good information. And if you really go down the rabbit hole, I'm telling you right now, you'll have a lot of trouble coming out. When it comes to GPU computing, it is the fundamental technology behind machine learning and the deployment of AI to industry. Now, one of the things that I will say about AI is I don't necessarily think it's something to be feared. That's a subjective comment. It is something that complements business. And most importantly, particularly when it comes to things such as networks, when it comes to pattern and image processing, it is a way of putting eyes on the application. So it changes the way that we will do traditional data acquisition rather than just taking in Modbus registers, Modbus values, individual 10 hertz samples of data. We're now actually able to have a computer to see what is going on and make decisions based on that. There are other types of AI, such as language processing. There's AIs being used in drug discovery and toxicology, military applications, not to mention that banks have been using it for financial fraud detection by doing behavioral analysis on your transactions for quite some time now. So AI is a major development driver for business, particularly when it comes to training and then subsequent inference servers. So when we look at training servers, neural nets and AI are a major breakaway from the if and else analysis that have historically existed with traditional software. Big data sets, when I was talking about big data, those data sets, that historical information is now the data that is used to train machine and deep learning systems for AI development. So GPU computing is what is actually used to train the networks for subsequent rollout. And once those networks are trained, that's exactly how we have eyes on the application in order to be able to see all of the cars that are across a 10-lane highway. And having a bit of a closer look at this, there's only one car that I can see, which it looks like the system has missed. The next level of AI, it's not the next level, but it's the other side, is the inference application. When it comes to GPU computing, those platforms there and all of the processing power that they bring to the table, I'm going to say it now, they're not cheap. Some of those cards can be worth $15,000 to $20,000, and we've got motherboards that can take 3 to 4 of them. But once those networks are actually developed for use, they can then be deployed onto much more basic, much more entry-grade devices in order to actually carry out that function. And the social evidence behind this is exactly the same as when you take a photo of someone and let's say your Android phone or your iPhone has facial recognition and it basically tells you where the face is. So now that we've gone through all of the hypotheticals and all of the deep stuff about what can be done, we're going to look at 2 boards here. I'm not going to spend too much time going through all of the tech stuff on the side. We've got the ASMB 786. The big thing about this one, and probably the points that I will highlight at a glance, is that it's got the PCI Express expansion slots there. So you've got the means to run a PCI 16 or 2 times PCI Express times 8 cards. But the big thing about this one is, from a very, very high level, is that it's basically just an i7 capable workstation, 8th gen. So this is where you'd probably use that, let's say, for a smaller box, let's say for a workstation, let's say for a design and visualization application. Whereas when we look at something like the ASMB 975, I'm even going to go as far as saying that the photo of the board even looks intimidating, especially when you look at those dual sockets right there. This is the type of board that would not only take a Xeon 8180 processor, but it would take 2 of them as well. So when we think about those high performance applications, particularly when it comes to resource allocation and virtualization, this is the type of board that can basically stack up a single 4U rack mount, provide it with 56 cores, a few hundred gigabytes of memory, storage, and allow you to run multiple virtual environments in a single platform. There are other boards in the range in between, but I've basically sort of had a look at the lower end of the server side through to the biggest gun that we've pretty much got in the arsenal. So as we start to wrap up here, let's put some context around some of the case studies around it. Here we've got a documented case, in this case from Israel, about automated optical inspection. Now, to move through this one quite quickly, this one started to use automated optical inspection processes in order to inspect the ever-shrinking circuitry that comes out on PCBs. Now, that automated optical inspection, particularly with the right reference, with the right training data, is exactly what speeds up the operations in order to provide more throughput, more output, drive prices down, and subsequently become more competitive in the industry. We also have another application here that was done in China as a smart city application. Now, the key takeaways from this is that they were using GPU computing and high performance computing to do analysis of urban environments, including population behavior, in order to be able to look at existing systems, existing infrastructure, and look at ways to optimize those existing platforms in order to keep people moving with the lowest amount of delays and optimize resources where they need to be. We have another application here in Europe for airport baggage inspection. Once again, this is yet again another automated optical inspection application where where the need here was to take multiple platforms and consolidate them into a smaller amount of systems. So there was a lot of resource put into the individual systems before that was allocated out for the different applications. We also have the high performance computing now in medicine, particularly for gathering of hospital data that needed to be sent up to the cloud for offsite security, but also to provide information to the surgical robots, medical devices, the control towers, and also to take the clinical data that was taken from medical devices and store that up. So there, as you can see on the very right-hand side of the graphic in the bottom corner, there is a storage server as part of this solution. And the final case study that I'm going to highlight here is a preventative maintenance and early warning application, particularly for rolling stock. So they were using high performance computing here to do analysis of mechanical equipment on rolling stock train cars. So in order to be able to do preventative maintenance, get ahead of potential failures, schedule downtime, and the like. So It's time to wrap up. It's time to wrap up. We're getting very, very close to the end. I know that I've taken up a bit of time. In order to summarize, what we've covered is we've looked at the embedded platforms and we can see that they are evolving. Although I've spent a lot of time talking about the high performance side of things, embedded platforms have their rightful place and they are getting more and more powerful and they are taking capabilities lower and lower into industry, particularly when it comes to things such as inference for taking developed machine learning networks and deploying them to the field. But we've also taken, I think, what is a high level look at the current and the future applications, particularly when it comes to the workstations, the high performance computing, the high capacity storage options, GPU and AI applications. And most importantly, I think the biggest takeaway here is that as computing power continues to evolve, it's going to allow industry to put eyes on the application. It's going to change the way we collect data, even though there's going to be so much more of it. And we're not going to be looking at numbers and individual alarms anymore. We're going to be able to see things as they happen. So thank you very much for your time.